Okay, so just off the bat, I'm gonna talk about the structure of the video. In the video, I'm basically just gonna go down the grading elements, and then just go down through each subsystem, and then talk about like these shortcut ways and all that stuff. At the end, if there's anything left out that I can think of, I'll probably add it in. Okay, so the first thing on the list is the asset manager, and the asset manager is a singleton with two maps, one for the models, one for the textures. I had it all in one place just so that the user can easily access it and not have to call the other kind of managers if there would be any. So I have basically four main functions: load model, get model, load texture, and get texture. And the loading the model is basically just checking to see from the asset name if that model's already in there. Then if it is, then like just delete it. So clean it from memory, which is basically essentially an override because I'm always creating something. So then I get that file name, create it to a string just so I can put it all in one string, and then I use a system command with that command and set it to the C string so that conversion is called. And then because I know that there was a conversion, or else I think the conversion gives you out a crash, I use that Azul file. I do some string manipulation just to get the format name right, and then I create that model from that format name. Get model is just basically getting the asset name and accessing the map to see if there's anything there. If it's null, that means you haven't put anything in there, and because you're trying to get something, that means that it's pretty much the user's fault. So what I do is I have an assert that just says, model could not be found, retrieval failed, which is basically telling you that, check your spelling or anything like that. And then load texture is the same as load model. First I check if there's any need to kind of override or get rid of the previous data, and then create a new one. And then the same is for the get texture. Unload assets is just whenever when you delete the asset manager, you want to get rid of all of them. It's just basically just clean up code, and that's it. So the next thing I'm going to talk about is how the user uses the asset manager, and basically from that P2 content, which is just all those hookups that we took out from the what we allowed the user to use. On the load game content, that's when you would call the asset manager load, and you call in the file name and then what you want to call it, so you can refer to it for easier than just having to have those extensions and whatever. And an example of actually using after you've loaded it is in this bomb we have creating a graphics object in my graphics maker, which I'll talk about in a bit. But as you can see, it gets a model from the asset manager and from the texture. And so just to show that it does work, I'll just build it very quickly, and you should see a bomb as well as like a bucket and a floor. So there we go. So the next thing to talk about is the time manager. And my time manager has two stopwatches, one for the current frame time and one for the total time. And it should be noted that my freeze times are changed, my free buttons I should say, to the keypad subtract and keypad add. Subtract starts the freeze, and the plus, the add starts the frame increments. So I have a few accessors just for getting the times, returns the float for that time of the watch. And I have an update, initialize stopwatches, delete me, and that's pretty much the bulk of the time manager. So what initialize stopwatches does is it initializes stopwatches and it starts to tick. And in order, because the way we have to read is we have to keep ticking and talking, but we have to initialize them. So in the game load, I have it initializing at the very end because I don't want it to start ticking and talking when we're loading the game context. So it wouldn't make sense to have the time before the game load. And then the updating, what it does is it talks both timers that I have. Here's the game total time, so it's just adding the time in seconds. But again, I won't talk too much about the freezing debug because that's something you've made and it wouldn't make sense to go over it again. So the only one that's talked is the current frame time, and that's because you want to get the time between frames. And that's pretty much it for the time manager, and because it's a singleton, I have the delete, which just calls delete on itself. And just to show that it does work, oh, sorry, actually, in the update, this update is called in the game in the update, so it's in part of the game loop. I did it at the very first one. And just to show that it does work, I have the a game object just kind of spewing out the information. So the frame time, the total time, and everything. So I'm gonna pause it. As you can see, we just started it, so we got the frame time and the game time and the total game time is around the same. If I go to the next few frames, you'll see that the total time is actually now a lot more, and that's because the total time takes into consideration the pauses, whereas the total game time does not. So as you can see, it's consistent, and that's pretty much it for the time manager. And that's because of the next thing to talk about is the scene control, but because the scene actually has a lot of things, and by things I mean like a lot of managers, I thought the best way to go about it is talk about the scene itself, then the individual managers within the scene, and then the scene functions such as the changing between scenes and stuff. So the next thing I want to talk about is the scene. And a scene is pretty much what it sounds like, a scene. And so a scene has to have a setup, so that you can see so that because every scene has to have some sort of initial setup, or else why would it be a scene? I have an on scene end, which just gets called when the scene changes or is about to be cleaned up as the final scene, just so that the player can do some kind of things on the scene end if they need to, like cleaning up certain things. And basically, a scene is composed of an updatable manager, drawable manager, input, alarm, collision, terminable, and termination dumpster. That being said, inputables and alarmables and all that stuff is pretty much going to be scene dependent because of these collision managers. I have a draw scene and update scene, and pretty much all of the update scene does is calls update or processes on all the other managers. So the input manager, alarm manager, update manager, collision manager, terminable, in that order. And it also has a draw scene, and all these are pretty much accessed from the scene manager, because only one scene can be active at a time. And these are just getters. So that's pretty much it for the scene. Just to show you that the on-scene end does work and how to set up the setup function, I derived a tutorial level, which is derived from the scene, and that's basically in the setup. It's making a floor and the bucket, doing some set collisions we'll talk about later, and then we have the on-scene end. So just to clear up the memory that was set up on the setup. So there you go. That's pretty much it for the scene. Getter. So the next thing to talk about is the updatable manager, but in order to have an updatable manager, you need to have an updatable, and that's what I'm going to be talking about now. And the updatable pretty much has one real function, and that is to update. So this virtual void update is a callback function that gets called from the update manager, and it's virtual so that the game object derives from the updatable and gets the update callback. And then anything, therefore, derived from game object also gets that update function, and you can override it to do things that you would want it to do in a game. So these are shortcut methods. They're just basically calling the scene and registering or deregistering through the scene manager. But in the video, I'll talk about some shortcuts, and I'll come back to them probably later on. So now I'm going to talk about the updatable manager. It's fairly simple. All it has to be able to do is register an updatable or deregister an updatable, and process all the updates. So in this case, when I register, it checks to see if it's already in there. If it is, then do nothing, and that's because if the player asks to have something registered and it's already there, then it's already there. So there's no reason to do anything else. And deregister is the same thing, where if it doesn't find it, then it won't do anything. And if it does find it, then it removes it from the list. And update all that basically does is iterates through the entire list of registered updatables and just calls that callback function. And in order to actually show that this works, um, I have a bomb which is registered for updating, and all it does is writes to the console bomb updating, and the floor is automatic. All of these game objects are automatically set to update. So to show that deregistration does work, is in the constructor I'll actually deregister from update, and um, because it's an updatable, it inherits that shortcut too. So the floor shouldn't be saying floor update, and the bomb should be saying bomb update in the console. So there you go, bomb updating. Now if I don't remove this, just to show that it does work, it'll say floor updating as well. There you go. That's pretty much it for the update manager. Okay, so next thing to talk about is drawable manager, but we have to talk about drawable again. It's pretty much almost the same as updatable in the sense that it does the same purpose. So we have those shortcuts, which is register to draw, deregister to draw, and I have another shortcut called set graphics object, and that just makes it so that the user doesn't really have to. It kind of streamlines memory, I guess, in the sense that this function right here deletes that graphics object, so it cleans up what the previous graphics object was and then sets that new one. And the graphics object is just the visual representation of the drawable. So every drawable has a visual representation and therefore a graphics object, or else it wouldn't be drawable if it didn't have a visual representation. And like the updatable, it has a callback, which in this case is draw. And I have another helper function, I guess, or just helping a little bit streamlining. So instead of the user having to remember to do the graphics object and then render, it does it for you. All it has to do is just say render graphics, which in context, within context, suggests the game object you're in, because it is a drawable. And then the register just calls the scene manager to register and deregister. So the drawable manager is pretty much the same as the update manager. It registers a drawable to draw, or deregisters a drawable to no longer draw it. And it has a draw all, which just iterates through that entire list of active drawables. Just to show that it's just iterating through it. And for register, it's pretty much the same way as the update. If it's already in there, then do nothing because it's already in there. If it's not, then add it to the list. Same for the deregister. If it's not there, then why would you deregister it? It's already deregistered. But if it is there, then remove it from the list. And then draw just goes through the entire list. And to show this, I have a bomb that it has a graphics set. So it has a bomb model and a bomb texture. And when you play it, because it's automatically game objects are automatically registered to the updatable and drawable, which I'll talk about later. As you can see, the bomb is being drawn, and if I deregister it whenever it gets initialized, which in this case is by a factory, I should not be able to see it anymore. But I can still collide with it. Just to show you, I'll put a breakpoint on the collision. So it's just to show that it is actually just the drawing that's not done. Sorry if there seems to be a little lag, that's just because of the video recorder. So there you go. The bomb is being collided with, but it just has no visual representation. That's pretty much it for the drawables. Automatic. The next thing I talk about is the input manager, but I'll talk about the inputable first. Just like all the other inputables, it has to be able to register and deregister itself to the appropriate input manager. And in this case, these are the shortcut helpers, and they take in the key and the key type event. And because we're calling it from an inputable, it'll use this object. So that's why you only need to do the key and the key event. But it'll actually call this key type, because the scene manager takes in a pointer. to which inputable to actually register. So, in essence, an inputable has two callbacks, a key down and a key up, and it has a parameter for key so that when a key down event is going to be called, the input manager passes in the key that was key down, so you can distinguish between which key was pressed down. And again, just the shortcuts. So that's pretty much for the inputable. So the next thing I'm going to talk about is the input manager. An input manager holds key states for every registered key. So for instance, if I register for an E key key up, then it'll create a key state. So in order to talk about the input manager, I have to talk about the key states first. And the key state first basically just has an assigned key. So when you construct one, so key, you'll say, okay, so this key state is for an E, in which case it'll store that E into the my key. So that becomes the E key state, like mini manager, I guess you could call it. And it has register and deregister and update, and just kind of other methods for checking the key down and key up. So the way it works is basically on the key update, it'll check to see if there's any key down. So if the E is keyed, in this case, let's say going back to the example of being an E key state, it'll check to see if the E is down, and then if the E key is up. So the checking down looks at the previous state. If that's if the previous state was false, in which case it hasn't been pressed, and then the current one is true, that means there was a key down event, or there was a key down. So you iterate through that the list of key down inputables, I guess you could call it, for the E key, and calls their key down and passes in that in this example the E key. And for the check key up, it's pretty much the same, but vice versa. And register just checks to see if the inputable is already in that list. If it is, then don't do anything. If it's not, then register it, depending on the key event. And the same for the deregister, but again, vice versa. And that's pretty much all of what a key state does. Next, I'll talk about the input manager and how it utilizes those key states. Register. So the next thing to talk about is the inputable manager, and the inputable manager is very similar. The only difference is it has these key states that I talked about already. And basically, it has a few functions. It has is key pressed, which gives you back whether a key is being pressed or not at a certain frame. And then you have registering for input for some inputable what key, and then under what key event, and same for deregister. So what ends up happening is, again, that is key press just returns the state of the key at a frame. The update is going through every key state and updating those key states so that they get those previous states and they get everything recorded. The key states are the actual ones that call the updates. The input manager only calls update on the key states. And registering input is basically if there's no key state already, then create a new key state under the key that it's trying to be registered to, and then register that key state. And the deregister input is basically it tries to find the key. If it doesn't find the key, then that means there couldn't be a inputable in there, so it just doesn't do anything. And then it tries to deregister, and deregister basically gives back a bool in this case. And if successful, then that means if it's successful, then it's going to do this, where it checks to see if the key state is empty now because we just deregistered something, and if it is empty, then delete that key state and remove it from the list. And that's pretty much all the input manager does. It's very similar to the other managers. And just to test that, in this bucket, I have myself registering for input. And when when I'm destroyed, I deregister myself for input because I don't want to keep being considered for input if I'm already dead. And in this case, for a key down, I have it so that when you hit space, if the key bringing down is space, then it'll create a bomb, which is why I registered for the key space key down. So, sorry, really fast, I forgot to change something. There we go. So now you should see the bomb. I accidentally forgot to remove the deregister from drawing. Okay, so you should see a bomb. And now the bucket is the one that has the key states. So when I press space, sorry, I shouldn't say has key states. It's registered for key event. When I press space, the bomb should show up right around here. So I just press space and there you go. And just to show that deregistration also works, I'm going to go ahead and deregister myself right after I register, just to show that deregistration does work. And this spawning should no longer be called because I'm no longer being considered for input. So I'm pressing space and nothing happens. And that's pretty much it for the input manager. Cancel. So the next thing I'm going to talk about is the alarm manager, and first we need to talk about the alarmable. So the alarmable pretty much in essence only has a few things. It has callbacks, which is alarm 0, 1, 2. It has a dispatch, which is also a callback, but for the alarm manager it's used so that when an alarm is triggered, it sends in which alarm was triggered. And then based on that, it'll call one of these. And just to show you, a dispatch, it gets the ID and then it calls the corresponding callback. And it also has time triggers, which is a array of floats, and that just holds when an alarm is supposed to go off. And that's pretty much it for the alarmable. It has a bunch of shortcut functions: set alarm, get time remaining, add time to alarm, subtract time from alarm, cancel alarm, but I'll talk about that during the alarm manager because it involves the alarm manager. It calls the C. So the next thing I'm going to talk about is an alarmable. Alarm manager, sorry. And the alarm manager, sorry, wrong one. So the alarm manager has a few things to do. And one of the things, just like the other managers, registering and deregistering, where it takes in a pointer to the alarmable that we want to register, under what ID and how much time to register, or how much time from when it's set to have it go off. And then deregister is just the alarmable pointer, so whose alarm to deregister and then which alarm. And also have these natural feeling ones where you have to add time to the alarm, subtract time from the alarm, and in the alarmable there's actually a few that are just kind of easier than having it to be in the alarm marker. And for that one, it's get time remaining of alarm. Get time remaining of alarm basically gets that time trigger array and sees if it's -1. -1 being that it's inactive. That when I deregister or pop one off, and I usually set it to -1 just to show that it's inactive. So if it's inactive, then just return -1, so that's it's not active. Or it has already triggered. If not, that means it's active. So what we do is we get that ID time because I said that it's the time in the time trigger is when it was set off plus the amount of time. So subtracting the total time from that would give you the amount remaining, and that's really easy when you do it from the time triggers. and very cost effective. So the alarm manager has, again, I told you, register, deregister. It has add time to alarm and subtracting time from an alarm. And it also has update alarms, which just updates its alarm markers. And it holds a timeline of these alarm markers. And in order to further talk about alarm manager, I have to talk about the alarm markers. So as I said before, I have to talk about the alarm markers now. And the alarm markers are pretty much just as they sound like it's going to be. It's just a marker. It has an alarmable for that's interested in a alarm callback. Because when you register for an alarm, it creates one of these markers. So it stores which alarmable for what alarm. And it doesn't include time because it's sorted in a multi-map based on the time that it was registered for. So all it really does is just has a method that's called from the alarm manager. It's called execute alarm, and all that does is gets the alarmable, sets that time trigger to -1, saying that's done, and then call dispatch on it with the alarm, which just calls its appropriate callback. And that's pretty much it for the alarm marker. So for the alarm manager, I'm going to talk about how it actually works. Talk about how it actually works. So when you register, it just tries to deregister because when you register, it'll override the previous one. So if it'll try to deregister, if it's not there, then it just won't do anything. And then it creates a new marker with the alarmable ID and the time that it wants. And in the alarm marker, when you create that, it actually sets it to the time you want plus the current time, which will give you a future time or when it should go off. And when you insert it with that same kind of time reasoning, where you want it to go off in the future, as marked by the player. And when you deregister, it basically has to get it gets the alarmables time trigger for the ID, and it makes an iterator basically iterate lower to the lowest. I guess it'll create a range for the iterator where it'll look for all of the alarmables, or I should say alarm markers. Alarm markers that have that trigger time. That way, you're restricting how many alarm markers to look for, because you don't have to look through the entire list. And then, if it finds it with the same ID and the same alarmable, then that means that, okay, we found it, it's safe to deregister it. So it'll set that alarm trigger, the alarmable's trigger, as -1 for the time trigger for the ID, and then deletes it and erases it from the list. Update alarms is where it actually does stuff. And basically what this does is, because the multi-map is sorted by time, it'll look at the very first element, which should be the lowest one because it's sorted by time, and it'll see if if that's trigger time or registered time to call its callback is less than the current time. If it is less than the current time, that means that that alarm should be triggered. So we execute the alarm, and then we delete it and remove it from memory. And it'll keep doing this until it doesn't find a time in the alarm marker that's in the past. And then add time to marker is one of those additional ones that I talked about. So basically, it looks for the ID, and if it's not inactive, so if it's active, then it'll get the time until alarm, so the time remaining, and it'll deregister any an alarm if there is an alarm to deregister, and then it registers that alarm with a time to add, so that time until the alarm goes plus the time to add. And it's essentially just deregistering and registering for that new time. And the subtract time does the same thing, pretty much, except it subtracts it. So that's pretty much it for the alarm manager. Different time. So in order to show that it worked, I have a bomb that when it's initialized, it's going to set its alarm to 10 seconds. And when it reaches 10 seconds, it's going to go to the lose screen because the whole point of the game is to try to get the bombs within those 10 seconds. And if so, it'll spawn a new bomb, and then the timer starts again. So right now I have it just writing to the console how much time is remaining to also show that the remaining time works. So there we go. It starts out of 10, goes down. And once it goes to 0, it'll go to -1. Which means it's inactive, and then we're at the lose screen. So that works. And then just to show that adding time also works, I'm going to add 2 seconds to it. So it should start off at around 12 because I added those 2 seconds. So there we go, 12. And now it's going to go down again until it reaches 0, and it sets itself to -1. And there you go, back to the lose. And to show that subtract also works, I'm going to subtract that time from it. So it should be 8 seconds now. And there you go, 8 seconds. And that's pretty much it for the alarm system. Now to check. So the next thing I'm going to talk about is the collision system, but first I have to talk about the collidable. And the collidable has a few shortcuts where it sets the collider. That's the collision model, because every collidable has to have some sort of collision mesh. And then we have the collision world, which is the world of the collidable. And we have a few other shortcuts, which is just registering to the collision. So actually, I don't even think that's a shortcut. But basically all it does is it registers itself to its own collidable group, and a collidable group is just a group of C-class, which could be ships or asteroids or whatever, and it just holds a list of all the ones that are all of the collidables of that class that have been registered for collision. So that's what register does, and same for deregister, it just gets rid of it. And we have a static function, which is test collision pair, and that just checks between two collidables if they're colliding. And just to show that, it's basically just getting getting vectors and stating that they're actually vectors by using that fourth parameter as a 0. So you get the initial radius, you get the initial centers. You multiply by that world transform, because when you multiply the vector, it doesn't actually have any translation with it. So translation is completely disregarded at this point. And when you get the magnitude of the differences of the vector length, then that's the scale, because rotation doesn't affect the magnitude of a line or of a vector, and there is no translation added to it. So now that we've got the new, and for the same thing for the center, you can actually just multiply that by the world. That'll give you the new location of the center. And so the way you check the distances between them is you check to see if the distance, you check to see if the radius added together of the two objects are greater than the distance, or vice versa. If the distance between them is less than both of the radii added, then that means there is a collision. Else, there's no collision. So the next thing to talk about is a collidable group, which is derived from a collidable group base, and that's just to be able to have pointers to each of the collidable groups. So they're wrapped around this collidable group base. And so the collidable group base doesn't actually do anything. Again, it's just a wrapper. And the collidable group is just kind of storage for what registered objects of a certain class want to be considered for collision. So if I had a ship, it would be the ship collidable group, in which case I would register ship objects that want to be collided with, or deregistered. Registered or deregistered. And so again, the collidable collection is just a collection of that class, um, and that's pretty much all it is. That's pretty much all the collidable groups are. It's meant to just hold the objects of class C that want to be considered for collision. So the next thing I'm going to talk about is the actual kind of processors, because we have two different type of collisions. We have pairwise collisions between two separate classes, and we have also self collisions. So the way that they have to be processed is different. So that's why going on with the new collision system that I've implemented, we have the collision processor base, which is just to be able to store the different pair processors and single processors. And also we have a pure virtual, because every processor needs to have some collision test. And so, as you can tell, the only really thing of substance in the pair processors is just one function. It's just collision test. It also holds collision groups. So when you create one, because it's templatized class of class C1, C2 for pairing, so it could be ship and asteroid, in which case it'll get both of their respective collidable groups, because they're the ones you want to do collision tests with. And so collision test for pairs is just checking the first one of the first pair and then all of the other ones, and then moving on to the next one, and so on and so forth. So it does collision tests between every single different combination of, for instance, ships and asteroids. And if it does, then it calls the callback for each of those. And the callback is in the collidable. Sorry, collidable. And this has to be, and this is the collidable one, but this is the one that's not going to get called. The only ones that get called is you're supposed to do it like we did in teal, where if I have, for instance, a bomb, and if I want to do some sort of collisions with something else, then I need to have that other virtual function. So bucket example, for example. Oops. And so it's going to call that collision with the other one, because it's like ship or bucket, etc. And the single is pretty much very similar. It's just got a different collision test, and that's because it wants to check it wants to not check itself for collision, because you don't want to collide with yourself, and you also want to be efficient in which you're not rechecking combinations. So the first one, it'll pick the first one in the list, then check with every other one other than itself, move on to the next one, and check that one with any other one that hasn't been checked yet, and forward, and so on and so forth. And then if a collision does happen, it'll call that collision callbacks. And that's where the static test collision pair comes in, for testing between two objects in the collidable. And that's pretty much it for the collision pair processors and how they work. But now I'm going to talk about the collision manager. So now we're going to talk about the collision manager. And the collision manager actually isn't that much as it used to be in the previous collision manager. So we have the set collision pair, which just calls the sets a collision pair. We have the set collision itself, which is setting a single processor for that only one instance. And basically what the collision manager really does is just sorry about this. I gotta get rid of this. The only thing that collision manager really does is just process collisions. And by process collisions, I mean it goes through its collision processor list. So a collision processor collection, so those single or pair collision processors. And it goes through those and calls that collision test. And as I told before, the collision test tests between either like, depending on if it's a single or a pair. If it's a pair, it'll check a class in colliding with other classes that have been registered for pairwise collisions. with either set collision pair or set collision self. And the way it works is basically when you create a level, you have to say what collisions you want. So set collision pair is the bomb. The bomb. In this case, I want to have collisions between a bomb and a bucket. So I set the collision pair for a bomb and a bucket. And this is actually in the scene, as I said before. So set collision pair or set collision self, and that just calls the collision manager to set the collisions or set the pairings. And so I have the bucket and the bomb, and that previous other one was a shortcut. And now I should be considered for collisions. And there's one more thing you actually have to do before colliding, and that is registering a specific object for collisions. So a bomb for collision, and a bucket also has to be registered in this case because I'm looking for a bucket and a bomb collision. And when it's colliding, it should call back the collision regarding what other type it has been collided with. So that's going to be the increment bombs diffuse and spawn random bomb. And in this case, what it does is just when you hit a bomb, it's going to spawn another bomb. So right now I'm just showing that it does work. Okay, so there's the bucket and there's the bomb, and when I collide with it, it should break. Yep, so it does have a collision and it is colliding. Then it spawns a new bomb. Now so the video recording is making it a little laggy. Oops. So spawns a bomb. Get the new bomb. I didn't reach it. But yeah, so you can tell that it does in fact collide. And whenever you have an object being destroyed, you want to deregister that collision. Because it would make sense that you don't want collisions to happen if your character is already dead. And that's pretty much it for the collision system.